We're going to start the second half of chapter 22 by looking at the Claisen reaction. The Claisen reaction is our second general class of reaction. In this case, we have enolates that react with esters or related type of compounds. The key difference for this kind of reaction is that we do a nucleophilic substitution on a carbonyl instead of doing a nucleophilic addition. So in the simplest Claisen reaction, which is the one we have here, we've got ethyl acetate, and the ethyl acetate gets deprotonated, reacts with another molecule of ethyl acetate to form a beta-keto ester. So the treatment of ethyl acetate with the sodium ethoxide allows us to deprotonate that. We do a nucleophilic substitution instead of a nucleophilic addition, and our product here is acetoacetate, and this is just a different category of reaction, and so we want to look at this and come up with different syntheses we can do with it. Oh, and one thing I do want to point out here is that this is not a base catalyzed reaction because we do require a full equivalent of the base in order to do this reaction. So the base is consumed. Let's look at the mechanism. The first three steps of our mechanism are a nucleophilic acyl substitution. And this gets us our product, but then something else happens, and I'll explain that here in just a moment. So first thing is that we deprotonate at the alpha carbon on one of our molecules of ethyl acetate. That gives us our resonance stabilized enolate. That enolate will then react with another molecule of the ester, forming our tetrahedral intermediate. This tetrahedral intermediate then undergoes elimination, where we lose this ethoxide group. And so instead of doing nucleophilic addition, where we protonate the oxygen, we reform a carbonyl, and so now we have a beta-keto ester. Now, there are two subsequent steps because there's still base left over here. There's some ethoxide. That ethoxide will react with the fairly acidic beta-keto ester to deprotonate it. So we need to do a subsequent step where we add a strong acid, some aqueous acid, to protonate this, and then that will regenerate our beta-keto ester. And this is why it's not really base catalyzed, because the base that's regenerated at the end reacts with this moderate acid here. All right, so the net result is that we do nucleophilic acyl substitution, and so when we do this, we get the nucleophilic substitution where the enolate is the nucleophile, and then our leaving group is whatever the alkoxy group is on the ester, and that gives us again a beta-keto ester. So we want to look at number 39 and see what kinds of see if we can predict the product of a reaction. All right, so here we're going to draw the Claisen product from each ester that is formed. The way I recommend doing this is to write out all of this up to the carbonyl, and that is going to be your keto part. So all right, and then we'll do another carbonyl in the beta position, and then we'll put OET. So we'll put this part, and then attached to this carbon was new on this side of the compound, and so this carbon is here, and so we need to add CH2, CH2, and a phenyl. So we'll do CH2, CH2, and a phenyl group. And then that is going to be our product. Now, that didn't leave me a whole lot of room for this next one, but we will manage here. So on this one, again, I recommend drawing all of this up to this point. So we got a methoxy group there. And then, so up to our carbonyl. And then again, we're going to draw this carbon, the carbonyl, and this. So all right, and so we've got this carbon. We need to draw a phenyl with a methoxy group on it. And that is how we draw the product of this reaction. So let's look at the crossed Claisen reaction and other related reactions. In the previous reaction, we used two of the same molecule, and when we used two of the same molecule, we got a particular product. In this case, if we use two different carbonyl compounds, where at least one of them is an ester, then we can do a crossed Claisen reaction. Now, when doing this, it's kind of like with the crossed aldol reaction. If you just throw two different esters in there that have alpha carbonyls, it's not going to be a very useful scenario. But if we use that same limitation, where if we only have one that has an alpha hydrogen on it, then we should be able to do the Claisen reaction. So here's the Claisen reaction. This one doesn't have an alpha hydrogen, and this one does. And so only this one will get deprotonated. And when it gets deprotonated, it will react with this one, and we will get this particular beta-keto ester. All right. The other option is that you can do a cross-Claisen reaction between a ketone and an ester. And so here with a ketone, there's not really an option. There's not really an option to do nucleophilic substitution. So if you deprotonate this, it can react with this one. Now you'll notice this one doesn't have an alpha hydrogen, so it couldn't get deprotonated. But here you'll notice we have now made this beta dicarbonyl compound where one's a ketone, one is an aldehyde. So it gives us a couple of different options of types of molecules that we can make. We can make a beta-keto ester, or we can make a dicarbonyl compound where they're either both aldehydes or both ketones. There are some other useful variations that we can do, and these other useful variations allow us to make slightly different kinds of beta dicarbonyl compounds. And so if we use either of these two reactions, this one's called ethyl chloroformate, which is a chemical you should be very careful with, and diethyl carbonate, and either one of these has two potential leaving groups. And so if you do the reaction with this one, you'll lose the chloro group. So here, if you do it with the diethyl carbonate, you'll lose one of them, and you'll get a beta diester. Instead of a beta keto ester, you can get a beta diester. That is a useful way for making something like malonate, diethyl malonate. And then this reaction is useful because here we can make a beta keto ester, which we could potentially use in our acetoacetic ester synthesis. So once we make this, we could use this as a deprotonation site in our acetoacetic ester synthesis that we talked about in the previous chapter. Let's look at number 40 on our in-class assignment. So here we want to draw the product that's formed from a Claisen reaction with each of these starting materials. So you'll notice on this one, you need to find out which one has the leaving group or which one doesn't have a beta hydrogen. And so this one has a leaving group. They both have alpha hydrogens rather, but this one has a leaving group. So we're going to draw this one up to the carbonyl. All right, we're going to lose that ethoxy group, and then this carbon is going to be bonded to that carbonyl to make that diketone. So that is a very handy way of making a diketone. All right, here we've got this one has an alpha hydrogen and this one doesn't. This one is the diethyl carbonate that we mentioned on that last page of the presentation we were just looking at. So since this one doesn't have an alpha hydrogen, it must have the one that is a leaving group. So we're going to deprotonate here. It will react with there. And so I'm going to go ahead and draw half of this. So I'm going to do ETO carbonyl. And this is going to act as our leaving group. And then this acts as our nucleophile. So carbon, carbonyl, OET, and then we have a methyl. All right. On this next one, if we look at this one doesn't have an alpha hydrogen, so it can't be our nucleophile. It must be our electrophile. And this one does have an alpha hydrogen, so that will be our nucleophile. There, we'll deprotonate there. So we will get, again, I'm going to draw the part that is the electrophile first. All right, so we get that aldehyde. So this carbon is going to be this one here. All right, and that gives you that particular product. All right, and then on this one, we don't have an alpha hydrogen, so it must be this one that's acting as an alpha hydrogen. This one doesn't have a leaving group, so that must be the nucleophile. So I'm going to take this one, between chloro and ethyl, the chloro is going to be the leaving group. So I'm going to draw this ethoxy group first, so ETO carbonyl. All right, and then the chloro group is going to get lost, and then we'll have this carbon. And then that will be our product. Again, I prefer to draw, when I'm doing these Claisen reactions, I prefer to draw the one that has the leaving group first, get to that carbonyl, lose that leaving group, and then have the nucleophile on the right side. You can do it any way you want, but be systematic about it, and that will help you to keep track of what it is that you are, what it is that you are making and what it is that is reacting. All right, our next reaction is one that is called the Dieckmann reaction. And it is simply a Claisen reaction that is an intramolecular reaction. So the intramolecular Claisen reaction is the Dieckmann reaction. We can form 5 and 6-membered rings. If we go smaller than that, we get a little too much angle strain, and that's not going to be very favorable. And if we go larger than that, we get the sort of angle strain from having large rings, so like 7 and 8. You can, there's probably examples out there of doing it, but it's not going to be a very favorable reaction. So what we want to do is we want to look at how this reaction works. So here's an example where we've got a 1,7 or 1,6 diester. So if you look, there's carbon 1, 2, 3, 4, 5, 6. And on a 1,6 diester, we will be able to deprotonate at the carbon 5, and that will make a nucleophilic attack and substitution on the carbonyl, and that will come around, cyclize, and give us a 5-membered ring. If we use a 1,7 diester, then we have 1, 2, 3, 4, 5, 6, 7. On carbon 6, it will come around and react with carbon 1, and so 1 through 6 gives us a 6-membered ring. So we can do 5-membered rings and 6-membered rings. We just need to see what kind of diester. Again, when you're writing out these kinds of reactions, I definitely recommend numbering your starting molecule so that you can keep track of what atoms are where. And once you're done drawing your product, you want to make sure that you have taken into account all of the carbons and that they are connected to the correct other carbons. All right, as I mentioned a little bit ago, these intramolecular reactions are called the Dieckmann reaction, and they are one, they're very cool, and two, they are very useful. So let's look at the mechanism. This mechanism is going to be very familiar because we've already done the Claisen mechanism. So for the very first step, we do deprotonation at an alpha carbon. So we'll remove a hydrogen and an alpha carbon. That will give us a resonance stabilized enolate. We don't have the resonance structure here, but there is a resonance structure for this. We do nucleophilic attack of that enolate on the other carbonyl in the compound. We'll get loss of ethoxide, so we'll lose ethoxide. That will reform our carbonyl. And then we have to, and then it will, because we have ethoxide left over, we're going to deprotonate. And then we have to protonate by adding subsequent addition of acid. We have to add this acid at the end of the reaction. If we add at the beginning, then the reaction doesn't work. So let's look at this one. This one's kind of cool because we get two products on this one. So it says, what two beta-keto esters are formed in the Dieckmann reaction with the following diester? So first of all, let's look and see what kind of diester it is. I'm going to start here. 1, 2, 3, 4, 5, 6. Because it is a 1,6 diester, we're going to get a 5-membered ring. And so there are two possibilities. You'll see that it says there's two beta-keto esters. And so one of the possibilities is where carbon 2 gets deprotonated and reacts with carbon 6. The other possibility is where carbon 5 gets deprotonated and reacts with carbon 1. And it doesn't matter which one you do first. You can do either one first. I'm going to arbitrarily choose carbon 2 getting deprotonated and reacting with carbon 6. So what we're going to get all right, so here this is carbon 6, 5, 4, 3, 2. Remember, carbon 2 reacted with carbon 6. And then carbon 2 there's carbon 1 and the ethoxide on carbon 1. Now you'll notice on carbon 3, we have 2 methyl groups. And so we'll put those 2 methyl groups there. And so that is our first product. Now for our second product, we can draw it the same way. So we'll do carbonyl. We're going to have a 5-membered ring. All right. But this one, we're going to have carbon 5 react with carbon 1. And so carbon 1 is going to be this carbon in this particular molecule. So 1, 2, 3, 4, 5, 6, and then O-ETH. And so over here, that's going to be that O-TH. All right, now we need to put these methyls in on carbon 3. And so here we'll have these 2 methyls. So these are constitutional isomers of each other. And so they're very similar compounds. It's just the 2 methyls are in different locations. And that is how we do that Dieckmann reaction. Okay, so now let's look at the Michael reaction. I have a fondness for this one. I did this one probably a dozen times during a particular project that I was working on in grad school, and it's just it's a very cool reaction. So like the aldol and the Claisen reaction, the Michael reaction does involve 2 carbonyl compounds where one is an enolate and one is a carbonyl, but the one that's the other carbonyl is an alpha beta unsaturated carbonyl compound. And so so here we've got an enolate, and here is an alpha beta unsaturated carbonyl compound. All right. With this alpha beta unsaturated carbonyl compound, we're not going to do the nucleophilic attack on the carbonyl carbon. It's going to react on the beta carbon. So it will react on the beta carbon. And so this is an example where we do 1,4 addition, or what we referred to previously when we looked at organocuprates back in chapter 17. We called it conjugate addition. So conjugate addition or 1,4 addition. And again, that's where we add across the alpha beta carbon bond. Because that beta carbon does have some partial positive character on it, it's got a partial positive charge on it, we can do reactions at that beta carbon. And so an enolate can react with that. And let's look at a couple of examples. We call molecules that are alpha beta unsaturated carbonyls, we call them in this context a Michael acceptor. So the nucleophile is the enolate, and the electrophile is going to be the beta carbon on the alpha beta unsaturated carbonyl compound. And again, we call that a Michael acceptor. So this is our Michael acceptor. We've got that beta carbonyl. Again, there's a partial positive there because of the resonance structures. And then here we've got this beta dicarbonyl compound. This one is a diester. We deprotonate with this. This doesn't take much of a base, but we deprotonate that. And that comes in and reacts with this beta carbon. When it does, and we'll go over the mechanism in a minute, but when it does, we end up adding this and a hydrogen across the beta alpha carbon bond. Here is another example. This one's in a ring, still works even if it's in a ring. This nucleophile comes in, reacts with that beta carbon, and we get that new bond between the beta carbon and here. Now, you'll notice on the top one we had a diester, and on this one we had a beta-keto ester. So there's a whole bunch of options we can use here as to what our nucleophile is. With something like this that's a beta-keto ester, it gives us the option of doing hydrolysis and decarboxylation a little bit later. We'll look at that possibility. All right, but let's start with the mechanism. The first step is just like the mechanism we've seen in others of these enolate reactions. We need to deprotonate at our alpha carbon. That forms a resonance stabilized enolate. We don't have our additional resonance structures here, but they are there. So we deprotonate. This enolate will then react with the beta carbon on an alpha beta unsaturated carbonyl compound. And so nucleophilic attack on that beta carbon. That does generate a resonance stabilized enolate. That resonance stabilized enolate is then protonated with some ethanol, and then that gives us this compound. Now, this ethoxide will in turn come along and react with this, so we probably need to add a little bit of acid to finish it off. All right, but there's also a cool thing we can do, which is this. If we use that beta-keto ester as our nucleophile, we've got this, and if we do hydrolysis, we can do hydrolysis with subsequent decarboxylation to give us this compound. And this is a 1,5 dicarbonyl compound. We've got a methyl there. We could potentially deprotonate this and come in and do an intramolecular aldol reaction, which that's kind of cool. So those 1,5 dicarbonyl compounds are quite useful. Here is this is a hormone that is synthesized using this method of the the Michael addition. So here we've got an alpha beta unsaturated carbonyl compound. We've got a carbonyl that has a hydrogen that we can deprotonate. So it has an alpha hydrogen that we can deprotonate. We deprotonate that. This acts as a nucleophile on that carbon. So we form this new bond. So between here and this carbon, we form this new bond. And then through the magic of many steps, several steps, we can convert into this hormone, estrone. Pretty cool reaction. Let's look at number 24 on the in-class assignment. All right, so we want to see what product is going to be formed. It's very important that you identify what it is that is your Michael acceptor and what's going to act as your nucleophile. So look for the alpha beta unsaturated compound. That's this one. So that's going to be your Michael acceptor. And then this must be our nucleophile. This diethyl malonate is going to be our nucleophile. We're going to deprotonate that. It will react with this carbon, and so we'll end up saturating this bond. So we'll have a new bond between this carbon and that bridging carbon. So I think the first thing I would recommend doing is to draw this. All right. This carbonyl remains intact. And then we have a bond between this carbon and this carbon. And so this is going to look a little weird, but it will work. All right, and we could leave it like this, or we could even do, there are some other potential reactions we could do, but most importantly, that's a 1,5. So we get, now that would be a 4-membered ring. We can't do that, but we could potentially decarboxylate this. So we could hydrolyze and decarboxylate it. We'd end up with a carboxylic acid, and that might be a useful compound depending on the context. All right, so now let's look at this one here. We've got an alpha beta unsaturated carbonyl compound. So this is going to be our Michael acceptor. Here we've got a nitrile. It's a beta nitrile ketone. So this nitrile acts a lot like a carbonyl in that it's very electron withdrawing and helps to make this hydrogen acidic. So this is going to be our nucleophile, and this will be our Michael acceptor. So again, I recommend drawing this. So draw your Michael acceptor first. Carbonyl remains intact. All right, and so there is the alpha carbon and the beta carbon, so alpha and beta. And then we're now going to draw this carbon. And we'll go ahead and put that carbonyl there. So that is, we've got this. We just haven't drawn the cyano group there. So we'll put a cyano group right there. All right, there are options you can do with this once you've made this. You've got ketones, so you can do reactions on those ketones that are particular ketones. We've also got the cyano group, and cyano groups, as we have seen, there are options that we could do to react this cyano group. For example, we saw reactions, if we react this with diabal, we could turn it into an aldehyde. If we react it with an organocuprate, we could turn it into a ketone, which I think that's almost a magical reaction. We saw that one a little earlier when we talked about ketones. I'm sorry, when we talked about nitrile compounds. All right. So now we're going to look at the Robinson annulation. Again, the Robinson annulation is just an incredibly useful reaction. And this is like the last reaction that we're looking at in this particular chapter. It's very, very cool because it involves two of the reactions that we've already talked about in this chapter. So it's a ring-forming reaction that combines a Michael addition with an intramolecular aldol reaction. So like this, it involves enolates, and we form the carbon-carbon bonds, but we're going to do 2 reactions. And so sometimes people look at it and they think it's really, really too hard to do, but it's not bad. This is not a bad reaction. So we'll start with the Robinson annulation. It's an alpha-beta unsaturated carbonyl compound. And then here we've got a carbonyl compound that forms an enolate. And you may think, okay, well, we could just deprotonate that. We react with that and we'd be done. But there's an additional reaction that we can do, which is where once we have formed that Michael product, we deprotonate this, it reacts with this, and we do an aldol condensation reaction. And we get this carbon-carbon double bond. So let's look at the details. Or actually, we'll look at some examples first. And I think it's worthwhile to look at the examples. So look at the examples so you can see what bonds are being formed and how you can write it out so that you can write it out so that you can draw your product very easily. All right, so the great feature about this is that we form these new 6-membered rings. So we'll form new bonds between these and these. All right, so the product the product contains an alpha-beta unsaturated ketone. So we started with an alpha-beta unsaturated ketone, and we end up with an alpha-beta unsaturated ketone. So here is methyl vinyl ketone. Well, this one's methyl vinyl ketone. This one is and has an extra carbon on it, but you can do the reaction with either one of these. We're going to get a new bond between this beta carbon on this alpha-beta unsaturated carbonyl and the alpha carbon on this adjacent carbon, on the adjacent compound. And then here, this carbon, which is the carbonyl carbon of this ketone, is going to end up reacting with the alpha carbon over here to do our aldol condensation. All right, so recognizing what reactions are, or what carbons go to where is probably the biggest deal when we're doing this. So let's look at the mechanism, and the mechanism helps us to understand what's going on, and it also helps us to make sure that we know which carbons are bonding to which other carbons. So part 1 is very much the same thing as the Michael addition. And in fact, if I had given you these compounds before we talked about Robinson annulation, you would just stop here. So we deprotonate this alpha-beta unsaturated, or this alpha, it's not an alpha-beta, it's a beta diketone in this case. So we deprotonate this. That becomes a nucleophile. That nucleophile attacks our Michael acceptor, and we get this enolate. That enolate gets protonated, and so now we have a 1,5-dicarbonyl compound that has a methyl here. Well, that 1,5-dicarbonyl compound can further react. We can deprotonate this. All right, so we're going to take this 1,5-dicarbonyl, we're going to deprotonate this. And when we deprotonate that methyl, on this methyl ketone, we deprotonate that. This is going to now become a nucleophile. That nucleophile will then react with this carbonyl, which will give us this tetrahedral intermediate that we have now seen about 1,000 times. And we protonate that tetrahedral intermediate, which will give us our beta hydroxycarbonyl compound. Now, in certain cases, when we've done aldol reactions, we stop there. But this one is particularly prone to doing the next step, which is the E1CB elimination. So we'll do the E1CB mechanism. We'll deprotonate this alpha carbon, which will generate this enolate. It is a resonance stabilized enolate. And then we lose hydroxide to form our alpha beta unsaturated carbonyl. And that is the product of our Robinson annulation. Pretty cool. So this particular part is all about recognizing, starting with your products, recognizing which part is which, how to line it up on your piece of paper so that you get something that you can turn into your product, and then drawing the correct product. It's important that you keep track of your carbons, and so I have a method that I'm going to use to recommend this. However, this is not some sort of universal method, so I'm just going to encourage you to use it, and you can check it out. So when you're drawing it, I recommend that you set it up like this, where you've got your Michael acceptor over here on the left side, and put your hydrogen that's going to do the aldol a little bit later, put it down at the bottom, put your carbonyl here on the left, and then your alpha beta carbons up here on the top on the left. Then the other carbonyl compound is going to be over here on the right. We're going to deprotonate this one, make a new bond with this. We'll deprotonate this, make a new bond with this, and then do an elimination. So place your alpha carbon of the carbonyl compound next to your alpha beta, your alpha carbon of the carbonyl compound that's to become the enolate, which is this one. And then the alpha beta unsaturated, the one that's going to bond with it, put it directly adjacent, and just kind of set them all up there. You have a new bond between this and this, and you'll have a new bond between this and this carbon, and we're going to lose that oxygen and form a double bond. All right. So once you have that, I'm going to show you now how to write the draw out the compounds and label it so that you get the right compound. So we'll go over here. All right, so the way I recommend setting this up is this one is already set up. So we'll call this carbon 1, 2, 3, 4, 5, and 6. And so that helps us to recognize what are the 6 carbons in our new 6-membered ring that we're going to form. And so those are the 6 carbons. And so once you have that, everything else kind of falls into place. We don't need to label these other things other than to know that they're there. All right. So as far as what the product here is going to be, all right, so we'll have a new bond between carbon, or we'll do this one first. So the new bond between 4 and 5, and the new bond between 1 and 6. So we're going to have a new 6-membered ring. All right, so and this is that methyl that was on carbon 5, and here is the carbonyl that was carbon 2. There's carbon 1, and we have a new carbon-carbon double bond in between carbons 1 and 6. Now, I'm going to go ahead and number these. So carbon 1, 2, 3, 4, 5, and 6. And again, that is just to help us to make sure that we're identifying which carbons go where. And so that gives us our correct product for this reaction. Let's set this one up. So on this one, I'm going to go ahead and number these. So this is carbon 1, 2, 3, 4, and then 5 and 6. All right. So now we need to arrange this so it looks like this. So I'm going to do that right here. So this one is the same as that. So we'll have our carbon-carbon double bond, carbon-oxygen double bond, and then there's carbons 1, 2, 3, and 4. And then we'll do, here's carbons 5 and 6. Carbon 6 has a carbonyl. And then adjacent to that, we've got a phenyl group, which I am just going to write as C6H5 at this point. All right, and then this is carbon 5, and there's 2 more carbons on there, so I'll put those there. And again, I'm going to label these 5 and 6. So now, all right, so these 2 things are going to add together, again, in the presence of our strong base. Now we'll have our new 6-membered ring that we have formed. I'll go ahead and number 1, 2, 3, 4, 5, and 6. Carbon 2 will still have that carbonyl. Carbons 3 and 4 will not be unsaturated anymore. Carbon 5 has a bond there. We do have this ethyl that is still there. Here's carbon 6. Carbon 6, the bond between carbon 6 and 1 became a double bond. And then here we still have this phenyl, and I'm going to go ahead and draw it as a benzene ring now. All right. And so that is our product of this reaction. All right. Here we've got another one. They've switched positions, but we don't want to let that confuse us. So we are going to redraw this here in a minute, but let's go ahead and number it. 1, 2, 3, 4. And then we have this extra one. I'm not going to call that 5 because I want 5 to be on the enolate carbon, and then carbon 6 is the one that is going to get the aldol condensation. So that's carbon 6. Let's redraw this. All right, so carbon 1, 2, 3, 4, and oh, not 5. That one's not 5, at least not according to our method here. So there's carbons 1, 2, 3, and 4, and then we're gonna have a methyl on carbon 4, and then on 5, we'll do 5 and 6 here. 6 is a carbonyl. It's part of a ring. And there's 5. So we'll put 5 and 6. All right. So now we're going to make a new bond between 4 and 5 and 1 and 6. So we'll have a new 6-membered ring. And then we have the 6-membered ring that we already had. And I'm going to go ahead and number these. So 1, 2, 3, 4, 5, and 6. So it matches up to the 1, 2, 3, 4, 5, and 6 that we have here. Carbon 4 has a methyl group on it. The bond between carbon 1 and 6 is a double bond. We have a carbonyl on carbon 2. And that is it. That is everything to that compound. All right. I'm going to have to emphasize, if you want to get good at this, you're going to have to practice it. This is not something where you see it once and then you have it down forever. If that is the case, you should really think about a future being a chemistry professor. But if that's not the case, if you look at this and say, wait a minute, I'm not sure I get this, then you're normal. And what that means is you just need to practice. Okay. All right, I had to pause for a moment. There were ambulances roaring past my house. Not sure where they were going, but I live near a hospital, so not unusual. All right, this is the final page in chapter 22, and then we're going to do our last problem in chapter 22. Our last problem in chapter 22 is, again, about the Robinson annulation. So here we want to look at what can we do for retrosynthesis with the Robinson annulation. So what do we need to do this analysis? It turns out it's just like what we just did. It's about numbering the carbons and making sure that you keep track of those carbons. And then when you do that, it's pretty easy to figure out what our starting materials were. So when you're trying to analyze what your Robinson annulation is, locate the new cyclohexane ring that you formed. That cyclohexane ring is going to have a carbonyl on it and a carbon-carbon double bond that you formed in the process of doing the Robinson annulation. And so in this case, that double bond, that ring is right here. So that means that, so this was our carbonyl, and this is the carbon-carbon double bond. Now, this looks a little bit different than what we saw on the previous page because it's turned around. No big deal. We're just going to take that molecule and flip it around. And so when we flip it around, it now is in the same orientation that we had when we were looking at this a little bit ago. All right, so it still has that same orientation. All right, so now these are the two new carbon-carbon bonds that we formed. This was carbon 1, 2, 3, 4, 5, and 6. And so once you've got that analyzed, you can break it apart. And so we made these two carbon-carbon bonds, and so this is going to be our alpha-beta unsaturated carbonyl compound, our Michael acceptor. And then this will be our carbonyl compound that was the enolate. All right, so let's look at some of these examples. And when we do this, we're going to label them, and then we'll write out what our initial reactants were. So let's go over to in-class assignment. So on this particular molecule, here is our new six-membered ring. That means our new bonds that we formed were this one, which I'll just draw a little arrow going to, and that one. And since those are the two new bonds that we formed, it's worthwhile to go ahead and label these as carbons 1, 2, 3, 4, 5, and 6. And then that will help us to draw what our starting materials were. All right, so carbon 1, that one's just going to be the methyl vinyl ketone that we have seen. We'll do our retrosynthesis arrow here. So double bond, carbonyl, and methyl. And again, that's carbons 1, 2, 3, and 4. All right, now for this component, we've got that cyclohexane ring. And we want to draw the things that are already attached. We already have a methyl attached. We have a carbonyl, and we've got this interesting little methyl vinyl group over here, or isobutylene group, or isopropylene group, if we want to call it that. All right, and one more thing is that carbon 6 needed to start off as a carbonyl. So here we've got this this 1,3 carbonyl, or beta diketone, and that would be our starting material. Oh, and let's go ahead and number that because we're doing that. So that's 5, and this is 6. And I goofed up and made that 5 look too much like a 6. Let's try that again. That is 5. All right. Fortunately, on this one, we've got the same thing. It's already set up in the right orientation. All right, so we're forming those two new bonds. We got 1, 2, 3, 4, 5, and 6. So 1 through 6, and we're making a new bond between carbons 1 and 6, and the new bond between carbons 1 and 4. We're going to have that same methyl vinyl ketone. All right, so that one is easy. And then we'll draw this. All right, and we had a carbonyl on carbon 6, which is right there. And we'll go ahead and label these as 5 and 6. And 1, 2, 3, and 4. And again, that's just to help us recognize which carbons ended up over here. All right, on this last one, it's gonna make a lot of sense to take this and rotate it around so that we get it so it's in this orientation. So this is our new carbon-carbon bond that we formed, which means that this is the other carbon-carbon bond that we formed. And if that's the case, that means let's see, I'm making sure I labeled the correct one. Yes. So that means that this is our beta carbon, that's our alpha carbon, there's our carbonyl, and that this was carbon number 1. So carbon 1, 2, 3, 4, 5, and 6. We're going to take that and rotate it around so that It's just like this, where we've got 5 and 6 over here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and 6. So on carbon 6, we have a propyl. So 1, 2, 3. On carbon 5, we have an ethyl. So there's carbon 5. And between carbons 1 and 6, we've got this carbon-carbon double bond. And on carbon 2, we have a carbonyl. And again, our new bonds that we form are between carbons 4 and 5 and between carbons 1 and 6. All right, now let's do our retrosynthesis. All right, so here we still have that same methyl vinyl ketone. Carbons 1, 2, 3, and 4. Here's carbons 5 and 6. Go ahead and label 5 and 6. On carbon 6, we've got a propyl. 1, 2, 3. All right, 1, 2, 3. Carbon 5, we have this ethyl, so 1, 2. And on carbon 6, we had a carbonyl. So this will be our alpha carbon. Now, fortunately, if you look at this, this is just 1, 2, 3, 4, 5, 6, 7. That is just heptan 4-one. And so it turns out this 5 and this carbon here are the same. So we're not going to get any sort of weird other molecules as our product. So we deprotonate carbon 5. That would make the Michael react with the Michael acceptor over here on carbon 4, which is our alpha beta unsaturated. And then subsequently, we would deprotonate carbon 1. It would do an intramolecular aldol with carbon 6, and then we get the condensation, so we get the double bond between carbons 1 and 6. All right, well, that is the end of chapter 22. Not as long of a chapter, but there are some challenging reactions in there, so it may take you a while to study those and get those down. Stay tuned for chapter 23, which is coming up soon. It is a chapter on amines.